Okay. So again, picking up kind of from yesterday, talking about conditions when things are spontaneous, looking at the 4 circumstances depending on whether we have an endothermic reaction or an endo, or whether we have increasing entropy or decreasing entropy. We get 4 sort of boxes or temperature conditions. So temperature required for a spontaneous reaction. Okay. To figure out that sort of minimum or max temperature, we're kind of working back from a system being at equilibrium. That's why I have this set equal to 0. If you're at equilibrium, Gibbs free energy will be 0. Now, this is what we have. Anytime you have a phase change, if you're going liquid to gas, you're exactly at the boiling point. You are precisely at equilibrium between the solid and the liquid if it's melting, or the liquid and the gas if it's boiling. So that's an important point for me to just emphasize, that I sort of regularly wouldn't mention. Or you get a question, it's boiling, you're at equilibrium, Gibbs is equal to 0. So if you have that phase change, delta G is 0. If you solve for temperature, I'm not going to bother doing that math, you get temperature is change in enthalpy divided by change in entropy. Now I'm going to leave out the states. I'm going to put them in just for emphasis. Okay. This is now for the system, and for the system, everything here is system. Okay. And we got pretty much the same relationship we had before, except for we had different states. Previously, we had change in entropy of the surroundings is minus change in enthalpy of the system divided by temperature. Okay. What we're getting using Gibbs free energy is change in enthalpy of the system divided by change in entropy of the system gives us our temperature. Okay. Connecting the two, change in entropy of the universe is change in entropy of the system minus plus the surroundings. And this is going to equal 0 if we're at equilibrium. So the change in entropy of the system is equal to change in entropy of the surroundings, except for a minus if you're at equilibrium. Okay? This is just true at equilibrium, that the system and the surroundings are equal but opposite to each other. And that's how you get to 0. So that's how these sort of two connect. Okay? The change in entropy of the system has the opposite sign as the surroundings. So the change in entropy of the system is going to introduce another negative, which is going to cancel out that negative. So we're not changing what we had before, just the relationship we're using today is from the system's perspective in both cases. So let's retake a look at those 4 situations and dive a little bit deeper and sort of solve for temperature, not just when it's spontaneous. Okay. So this is kind of what we worked off yesterday. I'm not going to put in any states because everything is for the system. I'll color code things a little bit more today. Okay. The green that I put in the boxes will be for the enthalpy term. The blue will be the minus T delta S term. So in our first box, when both parameters are positive, the enthalpy term will be positive. The minus T delta S term in this first box, delta S, is positive. So minus T delta S will be negative, okay, because of the minus sign. So we're going to have a minus term that can be modified in magnitude by the temperature. So this was our high T box. Okay. We want a high temperature to make that blue part, the negative blue, big, as large as possible, so it cancels out the green. So in this box is where we have an endothermic reaction that is not helping it be spontaneous, but we have a change in entropy that is positive or large. So this is entropy driven. It's not the enthalpy that's driving this box, it's the entropy, the increase in disorder, which can allow this to be spontaneous. Sort of going catty-cornered, we have our low temperature box in order for it to be exergonic. Okay. This is where the enthalpy is negative, the delta H is negative, but the minus T delta S, that whole term, is positive. So we want to minimize the blue now. So we want low temperatures to minimize the blue. Okay. So this box is exothermic, okay, and the change in entropy is negative. Okay. We're getting more ordered, which is not allowing or not helping there being free energy. So what's driving this box is that green negative symbol, the fact it's exothermic. Okay. So this is enthalpy driven. Okay. That's what's giving us our free energy. In our exothermic, this box is exothermic, and the change in entropy is increasing. It's a negative delta S. In this case, both enthalpy and entropy are both driving this reaction. So there's no way you can stop it under standard conditions. So this is always. I'm not going to write in all temperatures. Okay. There's no reason to ever do any math in that box. We don't want to solve for temperature in that box because it doesn't matter. Okay. And if you actually solve for temperature, I'll highlight this down below, you're going to get a negative temperature. You have to realize that negative temperature is garbage. It's an always temperature answer. Okay. Versus in this box, if you solve for temperature, you're going to get a negative answer again, but that's also a garbage answer because the true answer is never. Okay. This box is endothermic, which is not driving free energy, and the change in entropy is negative, or there's a drop in entropy. The entropy is dropping. I'm getting rid of the change symbol, or the delta S is negative. Okay. So kind of summarizing the box you're in from the sign. When you get a temperature that is positive, you're going to get that in one of two circumstances. One of the ways to get positive is if both of the signs are positive, delta H and delta S. If both of those are positive, sort of jumping up to this relationship now, if they're both positive, your temperature will be positive. The both positives is the high T box. Okay, that's this box. Okay. The other circumstance that you can get a positive temperature is if both of the terms are negative. If they're both negative, they cancel out, you'll get a positive temperature. And if they're both negative, that's that low T circumstance. You're going to solve for the temperature, but the answer is that temperature or lower. Okay? Versus they both being positive is you've solved for the temperature, but the answer is that temperature or above. Okay? So when you get questions, under what temperature is this circumstance spontaneous? Okay? Okay. The math only gives you that number. Okay? You need to think, is it an always, a never, that temperature above, or that temperature or below? When you solve for temperature and you get a negative number, I would have hoped you didn't do it in the first place. Okay, that's a sign that you overlooked the understanding of the question. Okay, the math you got is meaningless. Okay, if you get a negative answer, okay, if the reaction is endothermic, okay, it's never going to happen. The correct answer is no temperature. If you solve for your temperature and it's negative and it's an exothermic circumstance, you're in the always box. And I would hope that you would do a little mental check first. Okay. Okay. Look at your signs. Figure out whether the sign is going to be positive. If the sign is going to be positive because you have 2 pluses or 2 minuses, go ahead and do the math. Okay? And then think, are you high or low? Okay? Look at the 2 signs in the question. If one is positive and one is negative, then there's no point doing the math. You're not going to think of the math. You're going to think of what box you're in. Are you in a always box or are you in a never box? Okay? And just answer, there's no possible temperature. Done. Okay? Or okay, all temperatures are going to be spontaneous. Again, there's no reason for math or calculations. Okay? So we're just taking this extra step now. Okay? Your previous homework, it was always going to be spontaneous and you were just solving for the T and you're just going a little further now. So let's answer one question and then you can practice this yourself. Okay? In the question, we're going to get the delta H and delta S and then not do more math until we think about whether we should. Okay. Now we're going to solve for something that we already know the answer for, and we'll see if it jives or matches. Okay. Okay. Determine the temperature which water will spontaneously turn into water vapor. Okay. Don't say it, but hopefully you know the answer to this intuitively. And I find it quite neat that the answer that we know is correct, using enthalpy and entropy, we can get to that same answer. Okay? 2 concepts that don't seem connected to boiling point will lead us there. Okay? It's always worth thinking of the chemistry. So visualizing liquid water turning to water vapor. So that's liquid water in equilibrium with water vapor. Liquid water our reactant, water vapor our product. Okay? And we can solve for that temperature taking the enthalpy change of this reaction, dividing it by the entropy change. Okay. I put in no system or surroundings, so we need the system in both cases. Okay. I didn't give any other data with this question, so we're actually going to predict both. Let's start to set up the first prediction. Okay. We can solve for the change in enthalpy of the system, and we can solve for the change in entropy of the system. Okay. So using data sheets, we're going to predict the enthalpy change. Okay. So I'm not going to write out the formula. It's products minus reactants. I'm going to jump right into enthalpy. So we have 1 water vapor multiplied by the enthalpy change of water vapor, 241.8 kilojoules per mole. Okay, I'm using an AP data sheet, but it's almost the same as the Chem 30 enthalpy change that you're probably used to. So that's our water vapor product minus the reactant, 1 water liquid minus 285.8 kilojoules per mole. And I believe I used Chang version 11 as my data source for solving this. So our change in enthalpy is a positive 44.0 kilojoules per mole. Okay, so that's our delta H. We need to predict our enthalpy change using standard enthalpy values. Okay, so we got a positive delta H, delta S. These aren't formation values. When you look up enthalpy and Gibbs, they're formations. But for entropy, it's absolute. Okay, so elemental forms aren't 0 anymore. Okay, we don't have any elemental forms, so we don't have to worry about that. Okay. So we're back to the gas first, and the standard formation for water vapor, sorry, the absolute entropy for water vapor, 188.7 joules per Kelvin per mole, minus my reactant, water liquid, has a lower absolute entropy. It's a liquid compared to a gas. We expect the gas to be higher. Okay. And I get a positive 118 joules per Kelvin per mole. Okay. So now we've got our two numbers. We don't do the math right away. We think about what box we're in. Should we bother doing the math? We have a positive and a positive. So yes, we're going to need the math. We're at 2 pluses. So when we do this ratio, we're going to get a positive temperature. So we're going to get a meaningful temperature, 2 pluses. Let's just flip back to what we just did. 2 positives are when we're in the both delta H and delta S being positive. So we're in a high T situation. We're going to solve for the minimum temperature. The temperature we solve for and above are going to be the exergonic situations. And we'll solve for that, again, that minimum. So let's see what the math gives us. Okay, we got to watch our units because we have joules in one circumstance and kilojoules in the other. So we have a positive 44.0 kilojoules per mole for our enthalpy change. For our entropy, we've got joules. So I'm going to turn the joules into kilojoules per Kelvin per mole. So 118, if we divide it by 1,000, we'll turn the joules into kilojoules. So 0.118 kilojoules per Kelvin per mole. Our moles cancel. We just rigged our kilojoules to cancel, and the only thing we have left is Kelvin. Kelvin is on the bottom of the bottom, so it's to the -1 to the -1, which would just be on top. -1 times -1 would be just 1. So I'm not going to write that out. And I get 370. Now, when you convert this to degrees Celsius, because that's what we're used to, I get 97 degrees Celsius. Okay? And the true answer will be 97 degrees Celsius or greater is the temperatures that this would be spontaneous. So what do we expect when we do this? We would expect to get 100 degrees Celsius. That's what we know as the boiling point of water. And using entropy and enthalpy, I find this fascinating that we can make a really good prediction on the boiling point of water from like entropy. How on earth does disorder and chaos lead to boiling point? Well, it does through thermodynamics. Okay, why are we off a little bit? We're using standard values. Okay. These standard values are derived at 25 degrees Celsius, and we're solving for a temperature that isn't at 25 degrees Celsius. So there's a little bit of error using our standard values and not being there. Okay, but it only led to a 3 degrees Celsius error. Okay. So we have both calculated the boiling point, understood the 4 boxes, and realized we're a temperature or greater. For practice, I've got a couple questions. I'll put one up right away, maybe quickly discuss. So I'll flip back to this, and you can get all of these online or flip back between these slides. So from Advantage to Workbook, and then a couple old questions I really like, and I'm going to leave the old ones up first for you to solve first and then come back to these. We've got a couple questions sort of just like what we worked on. You're given entropy data, you're given enthalpy data, and you're going to figure out those temperatures. So exactly what we did. You don't have to make any predictions. You'd want to look at the signs first, okay, before you solve them. Then number 37 from a different book is my favorite question. There's no one answer. It's really you could write an essay on this. Explain the following nursery rhyme according to the second law of thermodynamics. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty Dumpty together again. So I'm not sure what the exact answer is to this, but I'll maybe guide you a little bit. So Humpty Dumpty sat on a wall with high potential energy, and he fell off the wall to low potential energy. Well, potential energy is kind of like enthalpy change in chemistry. So there's a change in enthalpy when he fell off the wall, okay? And then he fell apart. You can think of what's going on in terms of entropy or chaos when Humpty Dumpty broke into a whole bunch of pieces. Okay? So we got that potential energy change, we've got the entropy change of poor Humpty Dumpty, and we know him falling was a spontaneous process, exergonic. And they couldn't put him back together again. So that must be an endergonic process. You kind of want to put all these pieces together and try to, articulate how this is following the second law of thermodynamics. So I don't think it was written in terms of the laws of thermodynamics, but you can sort of play with it in terms of the laws of thermodynamics.